So our last lecture here on thermodynamics brings together a lot of concepts from previous chapters and allows us to kind of pull a lot of these concepts together. So one of the things that we will be kind of referring back to is, again, thinking about the direction that chemical reactions will proceed. So we're going to tie together spontaneity, and remember that spontaneity is going to be delta G, that's our free energy. And then the directions of chemical reactions, that really was equilibrium constant. So we'll think about sort of Q versus K. So the first thing that we're going to do is build on the last concept that we talked about, which was thinking about this win-lose sort of scenario. And when you have situations where one thermodynamic parameter, either enthalpy or entropy, is favorable and the other one is unfavorable, these are going to be the ones that have a temperature dependence. And so at some point, that process will change from being a spontaneous reaction to non-spontaneous, or from non-spontaneous to spontaneous, and that temperature at which that happens is what we call the pivot point. So we're going to look at that quantitatively today. We'll also talk about the concept of reaction coupling, which is a very important concept in biochemistry, for example, to think about how we can couple reactions together to pull reactions forward that maybe aren't thermodynamically favorable. And then again, we'll tie together these concepts of spontaneity with delta G and then equilibrium with K. So conceptually, we only have a few problems that we're going to work through today. But again, one of them is how do we calculate this pivot point temperature? And then we'll talk about how we think about delta G when we're not at standard conditions. So a little bit of a laundry list of homework problems to practice as we wrap up this chapter. So again, thinking about this concept of a pivot point. Right? So again, certain reactions are going to have a temperature dependence to them because either enthalpy or entropy is going to be unfavorable. So again, if entropy is going to be favorable, we want to be helping that, and so we want to increase temperature. If entropy is unfavorable, we want to be diminishing its contribution, so those are going to be reactions that are spontaneous at low temperatures. So if we know that spontaneity is really determined by the sign of delta G. Again, if delta G is negative, a reaction is spontaneous. What we can do mathematically is when we set delta G equal to 0, we actually can figure out the temperature at which this changes. So mathematically, look at this and see if this makes sense to you guys. We take our standard thermodynamic equation here, and if we set delta G equal to 0, we can then solve and have delta G equals T delta S, and then solving for T algebraically just has us take the ratio between the enthalpy and the entropy. And again, that will give us a temperature at which we are going to be changing spontaneity for a reaction that has a temperature dependence. So let's just look at a chemical reaction here that we can think about that we've looked at, and actually a couple of different problems here. So again, we've got copper oxide reacting with graphite here to make elemental copper and carbon monoxide. So again, this is a non-spontaneous reaction at low temperature, but as we increase the temperature, we can actually make this process spontaneous. And this is actually a chemical reaction that's used to extract copper from copper ore. So if you're mining copper and you want to get pure elemental copper there, this is actually the chemical process that you'll use. So one of the things that we can actually think about here is reaction spontaneity, or predicting kind of the enthalpy and entropies of processes here. So again, if we think about what we already know about predicting things here, remember we can think about predicting and thinking about things being favorable or unfavorable. So I'm just going to kind of highlight here. If something is favorable, we're going to say that that's helping. If something is unfavorable, we're going to say that that's hurting. So in this case, we can actually look at the entropy. Remember, entropy is the letter S, enthalpy is the letter H. We actually can look at this chemical reaction and get some information about whether or not entropy is favorable or unfavorable. In this case, hopefully everybody can look and recognize that we are making gas molecules. So we are making more gas molecules. Gas molecules move more. So entropy in this case is going to be favorable. So first, let's actually go through here and think about what it means to be favorable or unfavorable. So again, if entropy is negative, that's unfavorable. If enthalpy is positive, that's unfavorable. So anything that is unfavorable, let's put in red here. Things that are favorable, let's color in green. So if entropy is positive, that's favorable. If enthalpy is negative, meaning we have an exothermic reaction, then that is going to be favorable. So in this case, because we have more molecules that are moving more, we're making more gas molecules as products, we know that entropy must be positive. Because this reaction has a temperature dependence, that tells us that it must be an endothermic reaction. And again, if that's conceptually a little bit confusing, make sure to go back through our last lecture kind of with our win-lose combinations and understand that we couldn't have a win-win combination here. We couldn't have enthalpy be negative because then that reaction would always be spontaneous at any temperature. When we have a pivot point problem, when we have a reaction that changes its spontaneity, that must tell us that we have one of those win-lose combinations. Win-lose combinations only happen in reactions that have a temperature dependence. Okay, so what we're going to do here is we're actually going to figure out what temperature this occurs at. Okay. So again, here is going to be the problem that we'll work through at sample problem 20.8. So I want you to think about this for a minute. I'm going to give you a few clues here as we start beginning to work through this. But again, we want to know what the temperature is at this process, that this process becomes spontaneous under. We know that the delta G is positive 8.9. Okay, so at this point, we want to know at what temperature we need to increase the temperature to. At 25 degrees, it's not spontaneous. So what temperature do we need to increase it to in order to figure out what the temperature is going to be? So think about this. How could we figure out what delta H and delta S are for this process? Okay, give you again a hint. This is a process that we used before. If we had a balanced chemical reaction that we could figure out delta H and delta S, maybe using something like an appendix that has some values in it. So I'll give you a minute, pause the video, try to see if you can work through this solution on your own. And if you need some help, just feel free, play the video and let the solution play out. So I know there's a lot here on this slide, but just highlighting what we have shown in gray here is stuff that we've already done. This is stuff that we've already, skills that we've already practiced, taking a balanced chemical equation, using delta H and S values from Appendix B in order to determine what delta H and delta S of the reaction are. This last little piece here was just kind of a proof of concept to show that if you take those enthalpy and entropy values and you put them in this equation, you actually can solve for what delta G is, and we do get, with an experimental error, the same value that's provided. But the reason that we did this was not to solve for what delta G is, it was to actually determine what delta H and delta S are, because we need those parameters in order to figure out what our pivot point is. So remember, this is our pivot point equation. When we take delta G equals delta H minus T delta S, and we want to go ahead and figure out what that pivot point is, we set delta G equal to 0. And then that's how we get delta H equals T delta S. Solving for T is going to put delta H over delta S. Important here, make sure that you have things in the right units. So whether you convert your entropy to kilojoules, or in this case, we converted our enthalpy to joules. I usually mathematically find that to be an easier process to do. Then you go ahead and solve and you'll get a temperature in Kelvin. Keep in mind, sometimes a problem might ask for the temperature in centigrade, so you'll have to do that conversion back from Kelvin to Celsius. But again, we can see we knew that we were going to have to increase the temperature here. Okay, right? We knew we had a process where entropy was helping us, so we wanted to increase the temperature. And this little plot here is going to just kind of highlight what's going on here. The colder we get here, the more non-spontaneous that process becomes. So as we heat up this process, we become more spontaneous. Okay, and what we just did in this problem was solve for that pivot point, solve for that temperature, and it's just below 80 degrees Celsius. Okay, so a couple more concepts here, and then we're going to wrap up with kind of a big picture concept that ties a lot of things together here. So again, sometimes reactions might be slow, And if a reaction is slow but it's spontaneous, we learned about catalysts in our kinetics chapter in chapter 16. That can take a reaction and speed it up. And remember, catalysts can't take a non-spontaneous reaction and make it spontaneous, but it can lower that hill to go over to make that reaction go faster. Well, what about if you had a reaction that was non-spontaneous? How could you help that process? Well, this introduces a concept called reaction coupling, and this is actually a skill that you've really seen before. Remember when we talked about Hess's law, and if this was enthalpy here, if we had two reactions, we could sum them together, and in that case, we would sum the enthalpies. That's all that we're doing here, is we're summing the free energies here to get an overall free energy for this process. So with this chemical reaction, we can see that some things that are produced are products in one reaction, and then they're reactants in a subsequent reaction, such that they'll cancel out, and when we sum this reaction, oxygen in this case would have been an intermediate in the process. And when we sum up the delta G's, we can see if we started out with a reaction that was non-spontaneous, by coupling it to a reaction that is more spontaneous, we can end up with a net spontaneous overall process. This is a huge process that happens in biochemistry all the time. We see a lot of reaction coupling to allow us to pull thermodynamically unfavorable processes forward. All right, so this last concept, and we have a couple of problems to work through this. There's going to be some parts of this that are fairly simple to think about, and then a couple of things that might hurt your brain a little bit as we kind of begin to understand these. So one of the things that we're going to think about here is thinking about integrating these concepts of spontaneity and then equilibrium and then reaction shifting. So this is going to pull together a lot of concepts that we've talked about. Do you remember when we used to do a Q versus K comparison? And if Q was greater than K, that actually meant we made too many products and the equilibrium would have to shift back to the left. So one of the things that we're going to realize here is that any time where we're at is not where we want to be. So Q is not equal to K. We're going to shift towards K. So again, delta G will always be negative if Q does not equal K. We're going to be favorably shifting towards equilibrium, but it might change the direction that we need to go in. So I'm going to highlight this first here and then a couple of times from now. If Q is less than K here, that means we can still keep marching in our forward direction to get to K. If Q is greater than K, that means some of our products have to reverse that chemistry and go back and be reactants, which means we're changing the direction of the reaction. So again, we're going to see that a couple of times here. I'll make sure to highlight it because it can be a little bit of a confusing concept. So one of the things that we're going to see here, an important equation that we're going to derive here, is delta G is going to be equal to RT times the ln of the ratio of Q versus K. Now see if this makes sense. If Q is equal to K, then this becomes a 1. The ln of 1 is 0, so delta G becomes 0. For a reaction that's at equilibrium, delta G is 0. And that's a really important concept to kind of remember in your brain, that when delta G equals 0, we are at equilibrium. So how far off we are from equilibrium has to do with the difference between Q and K. So hopefully this math makes sense, right? The ln of A over B can also be equal to the ln of A minus the ln of B. So I can separate these two terms here. And what we're going to end up getting to is a really important equation. I'm going to write it separately here. It's an equation that we're going to use. And that's delta G equals minus RT ln of K. And so this is a really important equation that we're going to see in this chapter and actually also in our next chapter. But what this equation allows us to do is communicate the relationship between spontaneity and equilibrium. Whether and how much. Okay, so we're going to see that connection both through this equation here with a problem that we'll work through and also with kind of a reaction energy diagram like we've seen before. So just kind of wrapping up this slide here again, if Q and K are very different, the reaction is either going to absorb or release energy as we allow Q to approach K. And again, if they're nearly the same, we're still going to absorb or release energy to allow Q to become K. But again, there's not going to be a lot of energy. Whereas if we are far away, there's going to be a lot of energy either required or released. Okay? So again, conceptually, here's one of these other tables. Again, you can memorize this kind of a table or you can understand it. Again, this table highlights the differences between delta G and K. So let's look at this here. If we've got a delta G that's positive, essentially we're going to have a very small equilibrium constant. Remember what very small equilibrium constants mean? They mean we live on the reactant side. So essentially that means there's no reaction going in the forward direction. However, if we were sitting at complete products, the reverse reaction would basically go to completion. Think about this too. Remember from Hess's law, if we reversed a chemical reaction, so if we reverse a chemical reaction, we are going to reverse the sign of delta G. So a reaction that in the forward direction is going to have a positive 200. If we flip that reaction, that delta G will all of a sudden become a negative 200. And that K is going to become very, very large. Again, as we get towards equilibrium here, and again, I want to make sure to highlight that this does not necessarily always mean that equilibrium is going to be equal to 1. But when we are at equilibrium, if K was equal to 1 for an equilibrium or for a process, that would mean that delta G is 0. So I'm going to say that again because it's really important to highlight. Every reaction has their own equilibrium constant. Okay, so again, if we're going to think about equilibrium constants, we need to make sure that we're remembering that every equilibrium does not necessarily have an equilibrium constant equal to 1. But going over to the flip side here, again, if we've got a very negative delta G, that means a very large K, that means our forward reaction is going to essentially go to completion, and essentially we're not going to have any of our reverse reaction. So we're going to have two problems that allow us to kind of think about this to wrap up this chapter. The first one is a molecular scene problem, and then the second one is just kind of a computational problem. So in our first problem here, we're looking at a molecular scene that highlights this generic chemical reaction. We've got A2, which is represented by these two black spheres, this diatomic gas, B2, which is this green diatomic gas. These two molecules react to make two molecules of AB, which is represented by, again, a green and a black sphere together. So they tell us that this is a spontaneous process, so delta G equals minus 3.4 kilojoules per mole. So the first problem asks us if the mixture that they show us in 1 is at equilibrium, calculate what K is. So this problem actually is not any different from things that we've done before. So why don't you go ahead, try to work through that problem, try to solve for what K is if we know that reaction mixture 1 is at equilibrium. Okay, so remember, in order to figure out things with molecular scene problems, that usually involves counting, right? So I've gotten written under each molecular scene here, what the concentration is of each species. So highlighting here, each molecule represents 0.1 atmosphere. So each time we see one of these, it represents 0.1 atmosphere. So if we've got two of them, we've got two of these guys, that means that the partial pressure of that gas is 0.2 atmosphere. Same thing for two greens that we see here. And then we've got 4 of these guys, 1, 2, 3, and 4. So that's why that one's 0.4 atmosphere. This is the one that they tell us is at equilibrium. So if I write an equilibrium expression, it's going to be the partial pressure of AB squared divided by the partial pressure of A2 times the partial pressure of B2. So I'm just putting these values into my equilibrium expression and solving for K. And for this particular problem, K is equal to 4.0. Okay, so we've had problems like this before where it was a, hey, equilibrium. If this is at equilibrium, where are these guys at? So we need to do the same sort of calculations for these guys, counting up molecules, figuring out how that relates to partial pressures. And now since we know these guys aren't at equilibrium, we're actually putting those values into the same equilibrium expression, but it's going to be solving for Q. Right? So we can use essentially the same expression, but now because these are non-equilibrium conditions, we're solving for Q. So for our second molecular scene, Q is equal to 0.44. So Q is less than K, so we are before our equilibrium. In our third molecular scene here, Q is equal to 36. We've actually gone past our equilibrium. So in this case, we're going to have to turn around and come back. There's actually another problem here that asks us to think about what it means to be at standard state. So again, what we're doing here is working through the second part of the problem here, evaluating the delta G values for the second and third mixtures as well as for what's at standard state here. So again, we've just figured out sort of what the Q values are for these guys. Again, if we figure out if everything's at 1 atmosphere, putting all of the ones into this expression solves and gets a Q equal to 1. So in that case, putting things at standard state, which means everything's at 1 atmosphere, for this situation also means we are before our equilibrium. So let's go ahead, and this is a situation where, again, that was stuff that, hopefully is okay for you guys to work through on your own. I'm going to walk you through kind of another level of thinking about this, and I kind of wanted to kind of go through that in a couple of slides here. So what I've got here is an energy diagram, and we're going to kind of be building our own energy diagram for this problem. But the first thing I kind of wanted to do here is highlight, if I take the K value that we just had, so this is a copy of the last slide there, just to have all of this information here. If I take what that K value was, remember we have this important magic equation, delta G equals minus RT ln of K. So R is going to be our constant that allows us to think about energy. So that's going to have units of joules per mole. Temperature is 298 K, and I'm going to take the ln of our K, which was 4. Put that in, and I actually get minus 3.4. That was actually what they told us that delta G was. So just kind of a proof of concept there that we did get the right K value. But what I'm going to do now is I'm going to create my own sort of diagram that looks like this for this process. So one of the things I want to highlight is what we're going to show. We're going to draw essentially something that looks like this, and it's going to be relating the energy of our system as an extent of the reaction. So this is kind of like 100% reactants here, 100% product. So that's what I'm going to show on the next slide, and we're going to actually create this for this reaction that we're working through. What you'll note here is that for something that is a spontaneous process where we go downhill in energy, we're going to start out at a free energy that's higher than what we'd end up with. And that delta G is again going to be 3.4 kilojoules per mole. Okay? So I've kind of drawn my own here. So here's that same sort of bracket. Okay, this is 100% reactant over here, 100% product over here. Okay, so the difference between this energy and this energy is going to be going downhill minus 3.4 kilojoules. So, but we know we don't go 100% to product. My K is not some infinitesimally large number. My K was 4. So somewhere around here is my equilibrium mixture. This is going to represent sort of the low point that we have here for this process. What I'm going to do now is I'm going to map on mixtures 2 and 3 here. So I want you to just kind of pause the video for a second. Think about where you think those points would be along the line. Where would I have a point that is before equilibrium? Where would I have a point that's past equilibrium? And what would that mean is happening for that process? All right, so let's take our first molecular scene here. In this case, we're going to have something that is before equilibrium. So if that's the case and we live here, we can kind of continue to march forward, doing the same chemistry that we're going to have here, getting us to move this Q equals 0.44 up to our K, which is 4. So in this case, we're going to keep marching forward, doing the same chemistry. So this reaction is going to continue to move forward. We're going to keep going in the forward direction. What about for reaction mixture 3? What does that look like when Q is equal to 36? Well, in this case, this line is going, or this point is going to be past our equilibrium point. We've gone too far. So not only have we gone too far, and it actually will be a downward slope to go back to where we need to be, but the problem is we can't continue marching in this forward direction. We can't fix this problem by having A2 plus B2 making more 2AB. We actually need to have some of those 2ABs go back and make A2 and B2. So the reaction has to reverse. If you've gone past equilibrium, you actually have to reverse that direction. So you turn back and go the other way. And the only way to make that delta G be favorable and go downhill here is to go in the reverse direction, right? If we continue to march forward, if we continue to do this chemistry as shown, that's not going to get us to equilibrium. That'll continue to get us further away from equilibrium. All right, so this is just taking that picture that we put together on the last slide and just kind of mapping it onto kind of the standard sort of textbook one that's in your book and in our notes here. Okay, so one of the things conceptually I want you to be able to think about is what it means for a reaction when Q is not equal to K. In both of these situations, it's actually going to be favorable to slide back downhill to get to our equilibrium point. But what's different is reaction mixture 2 can keep marching in our forward direction. Reaction mixture 3 actually has to reverse the chemistry in order to make for a reaction that generates our equilibrium mixture. All right, last problem here has us think about the same kind of a situation, but now thinking about just doing some math with it. So here's our problem that we have here. We want to calculate K at 2 different temperatures. Okay, they give us the delta G of both of these temperatures, and let me actually go and highlight here. I've got to fix one of these numbers. This number here is actually not 212, but minus 12. So let me go ahead and fix that one right now. So that's what that number is. So we want to go ahead and calculate what K is at both of these different temperatures when they give us delta G's. Okay, so they give us delta G values for the 2 different temperatures. Okay, so I'm going to give you a little bit of a hint here. Let's think about some of the things that we know. So again, the delta G for this process at 298 is minus 141.6, and it becomes less spontaneous as we increase temperature. That's something we've seen before. When it becomes less spontaneous as we increase temperature, that must mean that entropy is not helping us. Entropy is a losing component in this process. So delta S must be negative. So some of the qualitative questions I could ask about a problem like this is to actually think about what's going on from an entropy standpoint. We could have predicted that too, right? Looking at this, we've got 3 moles of gas going to 2 moles of gas. In our more molecules moving more sort of scenario, this is fewer molecules, right? So that's going to be unfavorable from an entropy standpoint. Unfavorable entropy is negative. Okay, so that was kind of a review of some conceptual things that we've talked about. But if we want to just do this problem and we want to calculate K, what we need to do is we need to take our equation, delta G equals minus RT ln of K, and we need to solve for K. If you need some help with this algebra, make sure to reach out sort of offline here. But we need to take E to the both sides in order to isolate our K. Okay, so that's going to allow us to get K is equal to E to the minus delta G over RT. So what we're going to do is we're going to solve for minus delta G over RT, take E to that, and then that'll get us to K. So try working through that on your own. See if you can get those values, okay? And then continue playing the video to check your work. All right, so I've done this in two different colors just to clearly highlight the one that's done at 298 and then the one at 973. Going through the math, we can get that delta G minus delta G over RT term is going to be equal to positive 57.2. E to the 57.2 is a very large number, 7 times 10 to the 24th, essentially meaning we're going to have almost 100% products. This is a super spontaneous process, largely favoring products, as we can see with this equilibrium constant. When we're at 973, it's still a spontaneous process, okay? But now we're barely on the product side. Our K is not very large, okay? So barely on the product side there. Okay, so hopefully that's pretty straightforward for you guys to see those numbers. The last little piece we're going to work through here is thinking about kind of equilibrium shifting. So this is again a Q versus K comparison. So they tell us that we've got two containers that are filled with gas. One we're going to keep at 25, one we're going to keep at 700. And keep in mind 25 is 298, 700 is 973. So we're going to keep two containers of gases, and they've told us the amount of gas that they put in there. We want to know, will any of these, or which direction, if any, will these reactions proceed to reach equilibrium? So again, give you a hint here. This is a Q versus K comparison. We just solved for what our Ks are at these two different temperatures. So let's figure out what our Q is, and for each of these situations, figure out which way we have to shift. So try working through that problem, pause the video, and when you're ready to check your answer, press play. All right, so just putting into our equilibrium expression the concentrations that they give us, and again, they're given as partial pressures, we get that Q is equal to 4. So in our first situation, if Q is equal to 4, that's much less than our very large K that we solved for at 298. So that reaction is going to proceed to the right, and we're going to make a lot of product. When we see our situation here at 973, K was equal to 4.5. So in this case, Q is almost equal to K. We're a little bit less than K, so we still are going to shift to the right, but it's going to be a very slight shift to the right. We're going to make just a tiny bit more product, but not that much. All right, so wrapping up chapter 20, our last lecture here on thermodynamics. Right, we're dealing with spontaneity with delta G. So we did a lot thinking about kind of spontaneity in different directions, and we talked about this qualitatively last lecture with melting ice or freezing water, and did our win-lose sort of comparison to think about the fact that at some point we do have a pivot point here. We do have a temperature dependence of either melting ice or freezing water. Clearly we know that. And we know that the pivot point is 0 degrees C, but we learned in today's lecture how we can solve for what that temperature is. And then lastly, we did connect some previous concepts, thinking about sort of a Q versus K comparison, right? So thinking about tying together equilibrium and spontaneity. So when we are not at equilibrium, we are going to have a reaction that's spontaneous. We're either going to keep moving in the forward direction to be spontaneous, or we may need to reverse the reaction in order to be spontaneous. So again, how far we are away from K, how the magnitude of the difference between Q and K will be reflected in the magnitude of delta G. And again, we can calculate some of these parameters using two sort of important equations. One that we didn't spend a lot of time with today, so don't worry about it too much. There was one extra problem that we could have worked through, and this is how we deal with non-standard conditions. But just a topic that I chose to eliminate for this learning unit. But this is an important equation I want you to know, or at least know how to use. You won't need to know it, it'll be provided for you, but it's an important equation that allows us to relate thermodynamics and spontaneity with equilibrium and reaction shifting. Okay, so a kind of a little bit more of a dense lecture to sort of wrap up our thermodynamics unit, but hopefully we'll be able to answer any questions you might have in our in-class session.